Hello and welcome to our presentation that will give you a quick overview of our paper, Taming Energy Consumption Variations in System Benchmarking. My name is Zakaria Ournani and I'm presenting this work on the behalf of all of my colleagues in the 11th International Conference on Performance Engineering, ICPE 2020. The motivation behind green software design and multiple actions to reduce the digital energy consumption, such as this study, is the tremendous yearly increase of 8.5% of the energy consumption of the digital sector, knowing that data centers alone were responsible of 2% of the extra CO2 in the air as reported in 2017. A classic cycle of green software design or any actions that aim at monitoring and reducing the energy consumption of a software is to prepare the app or a part of it, such as a method or an algorithm that run some experiments to record some metrics such as the execution time or the consumed energy, and then analyze those results and check if they meet our expectations and how they can be improved. The problem here when talking about energy consumption is how confident are we about the recorded energy consumption, especially if we are using software tools that will give fine-grained results against some accuracy. But even with very accurate tools, how trustful is the hardware we're using to achieve the exact same behaviors with the exact same consumed energy when running the exact same task? The answer is clearly illustrated in this case of study where we run the exact same application with the exact same data load about 100 times on 6 identical machines of the same cluster. Each volume plot represents the variations of the consumed energy of the 100 executions within the same node or machine. As we can see, the intra-node variations, which is the difference in energy consumption that could separate two executions of the same task on the same node, can be up to 10% in this example. Same thing for the internodes variation that show how large of a variation we can get when running the same task on nodes that are supposedly homogeneous and identical. Those variations are very impactful, especially when we're testing some small changes that could enhance our application or our method, let's say for 10%, which could be completely absorbed within the variation, which is very problematic. Thus, the objectives of our work are first to investigate the energy consumption variations on multiple CPUs and architectures by considering many identical machines of numerous clusters to give our experiments more sense and accuracy. Then, we identify a set of controllable factors on which one can easily act or tune to reduce these energy consumption variations without, for example, having access to the data center, physical data center, which also makes sense with the new trend of massively using the cloud computing. Finally, we report on some guidelines on how to conduct reproducible experiments with less variations, especially for research purposes where we need to mitigate these variations to achieve proper experiments and get less biased energy consumption results. Let's start with a quick overview of our experiments environment and methodology. This slide illustrates an example of our typical experimental setup where we ship every experiment benchmark on an app within a Docker container that we deploy on one of our Grid 5000 clusters machine, where we run it multiple times and record the RAPL energy consumption data using an HWPC sensor. The energy consumption data is then sent to a distant MongoDB for post-mortem analysis, and we use the SmartWatts backend in some specific cases where we need a fine-grained consumption results, for example, at a processes level. To have a decent statistical accuracy, we executed each of our experiments over 100 times, and we used a decent set of benchmarks to validate our results, such as the MPB benchmark suite, LeanPack, or StressNG. Moreover, the experiments were executed on a set of identical nodes every time, so we can confirm the results with multiple nodes in the one hand and compare the internodes variations in the other hand. In this section, we will talk about the CPU energy variations, the different parameters that are or may be responsible for that, and how to tame that variations. So there are many parameters that one that could be responsible for or amplify the energy consumption variations. Some of these parameters have been reported in some previous papers. We can categorize these parameters into two categories. The first one concerns hardware parameters that are very difficult to change or to interact with, such as the CPU temperature, the CPU architecture, the chip manufacturing process, or the position, or even the position of a node in a physical cluster, especially in the modern data centers that we don't have access to. In the other side, we have software parameters that we qualify to be controllable parameters that one could tune or configure to mitigate the energy variation during experiments, such as the CPU states, the operating system parameters, turbo boost, the testing or benchmarking protocol, etc. Now we'll provide you with some mainline information that we got during our study on how to tame the CPU energy consumption variations during experiments. Our first hypothesis concerns the impact that may have the benchmarking protocol or testing protocol on the energy consumption variations. So to achieve robust and reproducible experiments, practitioners often repeat their tests multiple times. We therefore aim to study the impact of the benchmarking protocol and identify how to efficiently iterate the tests with the least variations. We thus conducted experiments with 3 execution modes to investigate if one can give least variations or, at the contrary, causes more variations than the others. In the first execution mode, named normal, in this figure, we run iteration after the other without any special or specific actions between iterations. In the sleep mode, we order the machine to sleep after each iteration. And finally, in the reboot mode, we applied a hard reboot to reset the machine state after each iteration. This figure in this slide represents a statistical bootstrap method that we applied on a set of executions to create 5,000 randomly selected set of 30 iterations each from the set of the global of the total executions that we conducted on a high workload tests on the NPB benchmark suite. The figure shows that we are very likely having much more variations when running tests and experiments with the reboot mode, while running tests successively or with sleeps seem to be very equivalent, with causing much less variations compared to the reboot mode. What is to retain here is while rebooting the machine seems to be very convenient, as it is a hard reset to the node state, we should really avoid it, as it can be responsible of 150% of the extra variations, especially at high workloads. The second hypothesis is about investigating the impact of the processor features regarding the energy variations. In this experiments, we tried to disable the C states that provide the CPU with the ability of going across different consumption states, especially when a CPU core is idle. In this figure, we can see the effect of disabling the CPU C states at multiple workloads on the variation of the energy consumption. We can clearly notice the impact of disabling the C states when running a simple process application or method, as the energy consumption varies five times less compared to the default mode where the C states are enabled. One would notice that disabling the C states would cause the job to consume much more energy. Well, this is completely expected, especially that this test machine is a 32 physical cores machine, and disabling the C states would cause all the cores to stay at a high frequency state, even if they are not used or inactive. In a less powerful machine, this difference would be much less aggressive. But in any case, disabling the C states is not something to do in a production environment. So the purpose here is to disable the C states to conduct experiments where we need to know precisely the energy consumption, as for example comparing two versions of an algorithm and if the improvement reduces the energy consumption. So it's more of a thing to do in a test environment to have an accurate estimation of the energy consumption. Using that on a continuous production environment doesn't make much of a sense. While increasing the workload to 100% at the extreme right of the figure, the difference between disabling and enabling the C state is not that apparent. In fact, when we use the CPU at its full capacity, disabling or enabling the C states won't change much as all cores are being used anyway and will be at a high frequency state. For a 50% load in the middle, the difference is not that apparent neither, unless there is a better way on how to assign tasks on the multiple available cores, which is the subject of a further slide. But in any case, the impact of disabling the C states without any process assignments or pinning strategy gets lower when increasing the number of running process or threads. This matter has been discussed in a full subsection in the paper, and that you can check for more details. So what is to retain here is that disabling the C states is a good way to stabilize the energy consumption of experiments, as it can reduce the variation by up to 6 times at low workloads. As we evoked earlier, pinning or assigning the processes on the execution cores could have an impact on the energy consumption variations. To show that, we ran a 50% workload test on a two sockets machine with a total of 32 physical cores and 64 hyper-threaded processing units. We also considered 3 different pinning strategies. The first one, S1, tried to minimize the count of the used sockets. In this example, we fully use 32 hyper-threaded processing units on the socket 0 and completely free socket 1 from work. In the strategy S2, we omit the usage of hyperthreading by pinning the processes on physical cores, so every process could use the whole core alone, with the exception of the operating system jobs that could cause some context switches, but this strategy aims at reducing the context switches to the minimum. The third strategy, S3, aims at using each of the 2 sockets at half of their capabilities. Thus, we use 16 processing units on each socket while using only half of the physical cores. After running experiments with each of these 3 strategies, we got, as we can see in the figure, that while the second strategy tends to consume the least amount of energy, the first one gives the least variations among all 3. In numbers, even if S1 and S3 are very similar, S1 exhibits 30 times less variation than S3, while S1 is 4 to 5 times better than S2, while it only consumes 30 to 40 times, 40% more energy than S2. So what is to retain here is that choosing the right way to assign tasks on the different available cores or processing units can reduce the energy variations by up to 30 times, where using the least amount of sockets seem to be very, very advantageous, along with a good management of hyperthreading. The third hypothesis concerns the impact of the operating system on the recorded energy consumption variations. During our experiments, we have seen that we cannot just run a test, record the energy consumption and variation, and just compare it to the idle state to deduce the impact of the operating system. In fact, we noticed that the operating system has a completely different behavior when idle compared to when executing a task, and can even exhibit more variation when idle. Therefore, we used the SmartWatts backend to have a fine-grained consumption results and isolate the operating system consumption from the job's consumption. This figure depicts the Pearson correlation between the global energy consumption and the job's energy consumption in blue, and the correlation between the global energy variation and the job's energy variation in red. We notice that both of the energy consumption and variation are highly correlated to the job's energy consumption and variation, with the Pearson correlation coefficients of 93 and 85% respectively. So what is to retain here is that the energy consumption and variation is mainly related to jobs in execution rather than the operating system. Our fourth and final hypothesis is to investigate the impact of the choice of the processor on mitigating the energy consumption variations. Some previous papers have reported that the energy consumption variation is growing with the new versions of CPUs. This is one thing that we wanted to reproduce and confirm across the many nodes of the many clusters we have access to and that have different generations of CPUs. During those experiments, we couldn't conclude on the evolution of the energy consumption variations across the Intel CPU generations. However, one result that we identified in those experiments is that low TDP CPUs are more likely to cause less variation than high TDP CPUs, with up to 3 times less variations at low workloads. The other thing to talk about here is the internodes variations. If we summarize all of our experiments, we identified some parameters that one could tune or configure in order to mitigate the intranode variations at multiple workloads. But we kept an eye on the internodes variation while applying that configuration or tuning. However, it didn't have any impact on the internodes energy variations, which seemed to be very stable. Previous works have reported on up to 30% of the internodes variations between identical machines. An example of that can be seen through this figure where we were able to reduce the intranode variations with extra tuning and configurations, while the internodes variations wasn't really affected, which highly recommends using always the same machine or node for experiments and not trust nodes homogeneity. At the end of our paper, we summarized in a table a set of some efficient guidelines that one could use to tame the energy consumption variations at multiple workloads, with up to 30 times enhancements with a proper sockets and processing unit selection, and more than 5 times less variations when disabling the C states or managing the hyperthreading. Again, those recommendations and guidelines are only valid for experiments executed on the same node, not similar ones. So, to conclude, we conducted a wide set of experiments on a wide range of nodes with multiple CPUs to investigate the intranode and internodes energy consumption variations. We identified a set of controllable factors and parameters that one could easily tune or configure without having access to the physical data center, for example, which is the case for when we're using the cloud platforms in order to tame the energy variation and conduct more robust and accurate experiments, especially in some cases where the accuracy of the measure is more important than the measure itself. Finally, we provide a set of guidelines on how to achieve that variations taming at multiple workloads. The highlight of these guidelines and our study in general is to reduce and study in general to reduce the energy variations are the main enhancements that we got with multiple tuning and configurations to reduce the energy consumption variations at multiple workloads. Given different improvement ratios of 150%, 300%, 500%, and up to 30 times, with the possibility of stack up those configurations and reduce the variation and drastically reduce the variations depending on the application we're testing or the workload we're running, etc. So now comparing the energy consumption results or monitoring the energy consumption could make more sense and be much more accurate. So this is some useful references for more details, and thank you for hearing me.